Okay, so when we go to compute now a second derivative on a two-variable function, things get a little more complicated, you know. And the deal is, you know, the second derivative comes off the first derivative, and so that automatically we know is going to complicate it because we've got two, if you will, first derivatives, right? We've got the partial of f with respect to x, and the partial of f with respect to y. So you've got two already. You've got two first order derivatives, if you will. So that in itself is more complicated because now to do a second derivative, right? I'm going to have to do something with both of these. Well, it turns out that here's what we need to talk about. So let's just focus on this one. So I've got this first order with respect to x, and so you know those can have both x and y parts to them. You know what I'm saying? And so it makes sense, or we can think about doing, for the second derivative, we can do a derivative with respect to x, or we can do a derivative with respect to y, both, right? So off of this one, we can, if you will, branch off. So we've got a partial of f with respect to x, and then do another one with respect to x. And so, yeah, that's just doing the first order partial with respect to x, and then doing it of x again. But it's very well possible we could have something we could take the derivative with respect to y of, so yeah. And so that just means we take the partial of this first order with respect to x, but we take it with respect to y. Okay. It sounds probably more complicated than it really is, but yeah, so you've got two off of that one. Well, guess what? Got the same deal on this one. We can do the partial of y, partial of f with respect to y, and then do that with respect to y again. So take the partial of f with respect to y, and then take the derivative with respect to y again. Or we can take that partial with respect to y and then do partial with respect to x. And that's the way we want to denote it. That really means a whole lot to you, but yeah. So there's actually four possible second order derivatives. That's what they are.
What's the highest amount of orders are we going to go to?
What's the highest we're going to do? Probably zero.
Okay, good.
We didn't do a whole lot with third derivatives and fourth derivatives before, so we'll keep it to this. All right, so let's find the second order derivatives for f of xy equals x cosine y plus y e to the x. Well, of course, to do the second order, as before, you need first order, so that's where you start. Partial of f with respect to x, and then the partial of f with respect to y. So with respect to x, that part of it would just be cosine y, right? And then the derivative of that with respect to x would just be y e to the x, because you don't need product rule there. That's good news. Because the other one's in terms of y. So the derivative of that's just 1. So pretty nice. Now the partial of that with respect to y, well, it's x. The x is fixed, so it's x times, then the derivative of that would be negative sine y. And then here, partial with respect to y, x is fixed, so e to the x is fixed, so it's just the derivative of y, which is 1, so it's just e to the x, isn't it? Minus x sine y, I guess we could, right? C dx or e dx minus sine y. Minus x sine y. All right. But the second order then, we take each one of those and do a partial with respect to x and a partial with respect to y. So the second order of this one with respect to x, well, even comes down further, because what would that be with respect to x? What would be the derivative of that? Well, it's, y is fixed, so the cosine y is fixed. That's just a constant. Derivative of that's 0. On the other hand, this one is y times e dx, so the y is fixed. So we just have derivative of e dx, but e dx is e dx, so it's just y e dx. Second order, that one. But from that one, we also could do the partial of x, partial of f with respect to x, and then with respect to y. Well, that maybe complicates it a little bit, not too much. So now we're doing this one with respect to y. So what do you got? Negative cosine y. Sorry, negative sine y. Derivative cosine is negative sine. And then here, y e to the x, e to the x fixed, so it's just 1 times e to the x. How are we going to write that? That sound right? All right, then we do the same thing over here. We do the partial with f with respect to y, do the partial with respect to y. Usually, for whatever reason, they do that first, but and you'll see in a minute. There is other good news coming. So do the partial with respect to y of that. So the x is fixed, so it's just minus x cosine y. X is fixed, so that's 0. Derivative. So it's just minus x cosine y. Now we have to do it though the other way with respect to x. What does that give me? So that with respect to x would just be minus 1 times sine y. Y is fixed. E to the x, derivative with respect to x would be e to the x. So e to the x minus sine y. Okay. So those are the second order derivatives right there. Yeah, here's the good news. Do you notice something about two of those? Namely, the bottom two here? The same? That happens a lot. So the good news is on that, yeah, there is a theorem that states with certain parameters, as long as the function is defined, the derivatives exist, there's regular stuff, continue, and they're, we've got continuity where these are continuous. That's going to happen. The fxy, if you will, that derivative is going to be equal to the fyx. Those two come out to be the same. It's called Clairaut's theorem. And they'll reference that, so be sure. Call it that, all right. Clairaut's theorem of fxy and its partial derivatives. Get all this down here. F partial with respect to x, f partial with respect to y, f partial with respect to x, then of y, and then f y with respect to x are defined AB and all are continuous at AB. Here's the part we want to know. Then f of xy AB equals fyx AB. Yeah, so those two things usually turn out to be the same. And we could do different examples. Let's talk about a couple. All right, so let's verify the conclusion. Clairaut's theorem. For this function, f of xy equals y sine of xy. Well, what that means is to show that these two things turn out to be the same. So we start with the partial with respect to x. What would it be? Y cosine xy times another y, which is y squared cosine xy. With me there? Believe that? Little chain rule for that one. Is that okay? Now, in the conclusion of Clairaut's theorem, we do f of x, y. So now we take this one and do the partial with respect to y. Well, that's a product rule, so we got 2y times cosine of xy plus, so that's the derivative of y squared with respect to y. Then we reverse that and do the y squared times the partial of that with respect to y, so that'd be a negative sine. Sine stays the same, times the inside with respect to y would be x. X is fixed. So not a whole lot to clean up on that. It's just 2y cosine of xy minus xy squared sine of xy. All right, so the other part of the conclusion is fyx, do it in that order, so I can get it right here. Partial of f, so we start now, we do the partial of that with respect to y. Well, that complicates it right off the bat because you got a product, because you got y here and y there, so it'd be 1 times sine of xy plus, reverse it, y times derivative of that with respect to y. So cosine xy times x. Let's rewrite that. Sine of xy plus xy, cosine of xy. All right, so now we need to do y, that with respect to x. Nope, it comes out to be that. So that with respect to x, so we'd have cosine xy times the derivative of the inside with respect to x would be y. Then over here, okay, so a little product rule. So the derivative of that, let's just do those two together because y is fixed. So the derivative of that with respect to x would just be y, cosine xy. Plus then reverse that, so we have xy times the derivative of, I still didn't leave myself room. Let's do down here. All right, so derivative of that, so you got minus sine of xy times the derivative of the inside with respect to x, which would be y. So it doesn't quite match it quite yet, but notice what we can do. Yeah, you got 2y cosines xy, so that's 2y cosine of xy's. And then this, we clean that up a little bit, that would be minus xy squared sine of xy. Match. Ta-da. Okay. So you do enough of those, you're thinking, why do I do both of them? I can just do one of them. Which brings up the next little point I was going to make. Now, in this case, did it matter which one I did? No, it didn't really matter which one I did first because both of them are about equal as far as the amount of effort it took. However, that may not be the case in all cases. Look at this one. Let's think about this one. All right, so let's find our fyx, fxy. This was real sneaky. Okay. Fy, so this is the partial of f with respect to y, and then take that partial with respect to x. But, looking at that, so the first thing we would do would be that, right? Partial of f with respect to y. Is that going to be complicated? Well, for that it's not, but little product rule there. And then we'll have to turn around and do the partial with respect to x of that. So that's going to be, in, product rule probably will lead us to something else anyway. The point of this is, since fyx equals fxy, let's think about that one. This one, I do the partial with respect to x, which is, what will be the partial with respect to x of that? Well, y's are fixed, so that's fixed. That's 0. With respect to x, it's y. So what's f of xy? Now we do that with respect to y. So guess what? That's the same thing there. So anyway, sometimes one way may be easier than the other, so sometimes it doesn't matter. All right. Okay. Interesting little thing.